Good morning, everybody. This recording is for pre-algebra, chapter 4, lesson 3, prime factorization and GCD, also known as the GCF. We'll talk about that in just a second. So this is kind of review from last year, and when I mean last year, sixth grade math. So sit back, relax, but pay attention. All right. So as just a review, a prime number is an integer greater than 1 with exactly 2 prime factors, one in itself. And what I mean by factors are things that when you multiply them are things you multiply together. So I could say factors of 15 would be 5 and 3 because 5 times 3 is 15. I could also say factors of 15 would be 15 and 1. Okay, so again, they're numbers being multiplied together to get the number you're looking at. So some prime numbers are 2, 3, 5, 7, 11, 13, and 17. So those are all numbers that can't have two numbers multiplied together other than 1 in itself. So 1 times 2 is 2, 1 times 3 is 3, 1 times 5 is 5, 1 times 7 is 7, 1 times 11 is 11. There's no other way to get 11 with multiplying, all right, besides 1 times 11. All right. A composite number, on the other hand, is an integer greater than 1 with more than 2 factors. So ways that I can get 4 would be 2 times 2. And I could also do 4 times 1. I could do 3 times 2 for 6. So all of these numbers are the factors. All right. And then I've got 4 times 2 equals 8. I can do 2 times 5 for 10. 3 times 3 equals 9. So basically anything that's got more than 1 times the number to get that number. All right. So 9 has 3 and 1 and 9. 10 has 1, 10, 2, and 5. So basically anytime it's got more than 2, 1 in itself. All right. And just remember that 1 is neither prime nor composite. So don't get tripped up on that. 1 is neither prime nor composite. Okay, next up, we have prime factorization, and prime factorization shows a composite number, so something that's more than just 1 in itself, written as a product of its prime factors, i.e. a bunch of prime numbers multiplied together to get the composite number. And you're going to have to write these using exponents once you figure out the answer. Okay? Now, also, remembering those divisibility rules from yesterday's video is really going to help you because then you can try to figure out prime numbers that go into each of these. So let's go ahead and do number 72 together. 72. Well, it ends in a 2, so I know it's divisible by 2. So I'm going to divide it by 2, and I'm going to get 36. So 2 times 36 is 72, and you can check my math on that. 2 times 36 is 72, but I don't have all prime numbers. The thing is when you're doing prime factorization, you need to break all of the numbers down until you get only prime numbers at the end. So 2 is prime, but 36 is not prime. 36 is divisible by 6, just because I memorized that. 6 times 6 is 36. So I'm going to break 36 down into 6 times 6, but 6 itself is still not prime, so I got to break it down again into 2 times 3 and 2 times 3. So now everything at the end of my factor tree, because it's kind of like a tree, it's kind of like a reverse tree or upside down tree where the branches are coming off, right? Now I only have prime numbers at the end of each branch. I've got a 2, a 2, a 3, and a 3. So I'm going to circle them, and I've got 3 2s and 2 3s, which means I can write this as exponents like I did from the previous lesson. So since I have 3 2s because I was multiplying, it's not 3 times 2. It's 2 to the 3rd power times 3 to the 2nd power because I have 2 3s. Okay, because when we're multiplying, that's when we can get exponents. All right, let's move on to the next one, 121. Well, 121 is easy. Most of you guys should know. It's 11 times 11, and 11's prime. Remember, it was an example from the previous slide. So I have 11 times 11, which is 11 squared. So that is doing it as a prime factorization, which is just 11 squared. All right, because 11's prime. So 11 squared is still 121. This is still 72. All right, so all of the answers we're getting still equal the original number. It's just we're writing them using prime factorizations. And this is going to come in handy way later when you're simplifying polynomials, when you're simplifying all of this other junk, knowing this now, even though it's going to feel different when you're actually using it later, is real handy, okay? All right, so 225, it's divisible by 5 because it ends in a 5. So once you divide it by 5, you're going to figure out that you get 45 out. So 5 times 45 is still 225, but 45 isn't prime, whereas 5 is prime. So I got to break up 45. That's 5 times 9. Well, 5 and 9 are both prime, so I'm ready to circle my prime numbers. Oh, wait, no, I'm sorry. 9 is not prime. Blah, blah. You can break it down into 3 times 3. Now, 3 and 3 are prime. So now I can circle some prime numbers. There we go. I'm catching up to myself. You guys see that? I'm making it there. All right. So I have 2 3s and 2 5s. So 3 times 3 times 5 times 5 is 3 squared times 5 squared. And just remember that to the second power, another way to say it is squared. All right. Whereas to the third power, right here, just a little side note, means cubed. Just a refresher from yesterday, okay? All right, well, this one I kind of just broke down for you quickly. Since this ends in an even number, I know it's divisible by 2, so I divided it by 2, and I got 180, or 118. And since it also ends in an even number, I knew it was also divisible by 2. Now, 59 is not divisible by anything else. It's not divisible by 3 because when you add up 5 and 9, you're going to get 14. 14 is not divisible by 3, which means it's also not divisible by 9, which means it can't be divisible by 6 because it's not divisible by 3. It doesn't end in an even number, so it's not divisible by 2, and it doesn't end in a 5 or 0, so it's not divisible by 10 or 5. So guess what? It is a prime number. All right, time to start just memorizing those prime numbers. So what do I have? I have 2 times 2 times 59, which is 2 squared times 59. And remember, these still equal the original number. So if you were to go through and, do some math, you're going to find out that you get the number back out. All right? So each number has its own distinct prime factorization. Every number does. It's either a prime number, so it's 1 times itself, or, it's very distinct. You can't get 72 any other way using prime numbers than 2 cubed times 3 squared, okay? So just know that every single number has its own distinct prime factorization. No 2 prime factorizations are the same for 2 different numbers. Okay, moving on. Ready? Okay, so now let's go ahead and find the GCD/the GCF. All right, and this stands for the greatest common factor or greatest common divisor. They mean the same thing. Remember this so you don't get confused. If they're asking you for the GCD, they're also asking you for the GCF because the GCD and the GCF, same thing. Now I'm going to show you first the way I taught you how to do it in 6th grade math, or at least how you may have learned it in 6th grade math. And then I'm going to show you how to do it with the prime factorization trees from the previous slide. Okay, so the first thing you do is you're making an upside down wedding cake. So we have upside down cakes and we have upside down branches and trees for this one. So what you got to do is you got to figure out a prime number that goes into both numbers. Well, both of them are divisible by 2, in this case 8 and 20. Both of them are divisible by 2, so I'm going to put a 2 on the outside and then divide each number by that number. So 8 divided by 2 is 4, 20 divided by 2 is 10. So now I have those two numbers. Well, what's another prime number that goes into both 4 and 10? Well, that's 2 again. Divide by 2, you're going to get 2 and 5. And now since these are prime and they have nothing in common, I'm going to make a G around the numbers on the left side of my cake. And I'm going to make a G for greatest. All right? Later on we'll be doing an L for least, but for right now we're doing a G for greatest. So those are actually, when I multiply those two numbers together, it's going to be my GCD/GCF. So 2 times 2 is 4. So both numbers are divisible by 4, and it is the biggest number that I can divide both numbers by and still get a non-remainder answer, okay? I could divide both numbers by 6, but I'm going to get a decimal or a fraction. I could do, hold on, Miss Michelle's here. Okay, I'm back. So again, you could divide 8 and 20 by like 5. But both of them, 20 will give you 4, but if you divided 8 by 5, you're going to get a decimal or fraction. So that doesn't work out, whereas 4 is the biggest number possible where you can divide both 8 and 20 by it and still get a non-decimal, non-fraction answer. Okay, so now let's go ahead and do this with something that's got some letters in it, because you guys are in pre-algebra, so the letters will be there. So let's go ahead and make our cake. And a number or letter that goes into both 12r to the third and 8r is r. R goes into both of them. They're both divisible by r. The thing is it only goes in once. So I'm going to remove one of the r's from the area. And so if I remove one of the r's, I have 12r to the second and 8. Because the r here is gone, and one of the r's there is gone. Okay? You guys see that? So basically you're just removing one of the r's from both of the numbers. Okay? So now I'm left with 12r to the second and 8. So you can't remove any more r's because both of them don't have r's. 8 doesn't have an r anymore. So we can't remove any more r's. So that 12r to the second, that r to the second with the 12 is just going to have to stay there. And that's it. All right? So, but what's the number that goes into 12 and 8 that is prime? Well, you guessed it. That's 2. So 2 goes into 12 6 times, and 2 goes into 8 4 times. So I'm left over with a 6 and a 4. And guess what? 2 goes into 6 and 4 again. So we have r times 2, which is basically 4r. All right? So that's the GCF/GCD is 4r for 12r to the third and 8r. All right? So if I were to divide 12r to the third by 4r, I'm going to get something that doesn't have a decimal. And if I divide 8r by 4r, I'm still not going to get a decimal. And this is the biggest number possible, which is why we're dealing with the greatest. It's the biggest number possible. All right. Now let's deal with 15m to the second n and 45m. So let's make our cake. What goes into both 15m squared times n and 45m? Well, m does. So I'm removing an m. This m goes away because I'm minusing one m. And this one of those m goes away just to leave me with one m. And since it's one m, we don't need to put an exponent. Now there is an invisible 1m exponent there, and there always will be because m to the first power is m. All right? So now what can I pull out of 15m, n, and 45? Well, you guessed it, a 5. 5 goes into 15 3 times. The m and the n still there because I didn't divide by them. And 5 goes into 45 9 times. There is still another prime number that goes into 3mn and 9. That would be 3. So we're going to divide by 3, and we're going to get an mn at the end and a 3. But since they have nothing in common, I can't go any further. So I'm going to make a g around m5, 3, multiply them together, and I get 15m. Okay, last thing I want to show you is how to do this with the prime factorization trees. Okay, so let's do this with 8 and 20 since we already know what the answer is. We can double check our math, but using a different method. So I'm going to make a tree for both of these. 8 turns into 2 times 2 times 2, and 20 turns into 2 times 2 times 5. So I'm going to circle the things on the trees, on both trees that are common. So I have 1, 2. I have 1, 2 on both of them. So and I have another 2 on both of them, but they have nothing else in common. So I have 2 2's in common. 2 times 2 is 4. Well, if you look back to the previous one, actually, hold on. If you look back to the previous one, it is 4, right there, okay? So let's move back to where we were. Oh, that's a little too far. Let's move back. There we go. Okay, so we do end up with 4 as the GCD/GCF. Remember, they're the same thing. And let's do it now with some numbers and letters. This one's going to be a little crazy, so try to keep up with me, okay? So let's do it for 36m to the second, n to the third, and 15m n to the second. Let's make some trees. So I made the trees for you, and they're a little crazy. 36 breaks into 6 times 6. The 6's break into 2 times 3. M to the second breaks into m times m, and m to the third breaks down into mn times n squared, where n squared breaks down into n times n. 15m n to the second breaks down into 3 times 5, and m and n times n. So now let's circle the things they have in common on both trees. Both trees. Well, we have an m on both trees, we have an n on both trees, and we have a 3 on both trees. But that is it. Okay, so we're going to pull the m's and the n and the 3, but we only need them once. So the answer is going to be 3m. Oh, there was a second set of n's. Sorry, there was a second set of n's. So it's going to be 3m n to the second, and that is the GCF/GCD. All right, I am done. Hope this is review. Good luck with those letters. They're a little crazy. All right, bye.